So we are looking at an image of the Nadivalaya. Nadivalaya, it's an instrument in Jaipur Observatory, and we are now looking at it from west. We are to the west and we are looking at this instrument. And this is then to the south and this is to the north. So it has actually two faces. Right now we are seeing just from the side, so it looks a little peculiar. Now this is the south facing side. This side, if I am showing here, this is the south facing side. It has a dial clock on it, and you can see that this is tilted from the vertical by an angle. And so this is done in such a way that this angle, you can also see that there is a rod projecting out from it. There is a rod projecting out from it. So the rod projecting out comes out here as well as here, let's say. So this then, if this makes a triangle, the angle in this triangle, this should be equal to the latitude of the location. So that is how it is built. And so this is the south facing dial. So this is tilted forward like this. And you have a dial plate here, and this is the north facing side, and you have a dial plate here. So this is tilted backwards like this.
Is there any specific reason for the tilt? Like if you see the previous picture, so is there any
yes. This
reason
this
for
image.
this? Yeah.
Yes. And you also see that this tilt is the same for this face and this face, right?
Exactly.
Both are exactly the same angle. So this is tilted in such a way that from the vertical it is tilted by a particular angle. So it is tilted by an angle which is actually equal to 90 minus the latitude, and therefore the rod which goes through it, so this angle then becomes the latitude. This is latitude. So you are asking why it is built that way. So this is now a sundial. Okay, so the sundial, the clock faces that we have here are going to tell us the time. Now this rod, as I said, was done in such a way that it is by an angle equal to latitude of this location. This makes it so that this rod then is parallel to axis of rotation of Earth. It becomes parallel to axis of rotation of Earth. So on the surface of the Earth, anywhere that you are, let's say we take the northern hemisphere, anywhere you are, you put a rod with an angle equal to latitude of that location, it will then become parallel to axis of rotation of Earth. And then these dial plates are perpendicular to the rod. So these become parallel to the equator. So these become parallel to the equator, and so this shadow of the rod that we see here, the shadow of the rod swings. Actually in the morning when sun is in the east, it will be towards the west, and then it will come noontime and it will swing here. So this then works like a clock, and now we still haven't answered why it is done this in this peculiar way. By seeing that you put this parallel to the equator, the shadow is then moving parallel to the equator, right? Because of this construction. Shadow is moving parallel to the equator. And when the shadow is moving parallel to the equator, we can easily calibrate our clock. In equal intervals of time, the shadow will move equal distances. It doesn't happen if you put, let's say, if you put a pen, if you put, let's say, a gnomon, vertical gnomon. If you have it, you can see the shadow of it, let's say sunlight shadow. Then in the morning you'll have a long shadow. It'll run fast, then it'll slow down and there'll be a shorter shadow in the noon. Then again it'll pick up speed and there'll be long shadows. So it will be a slightly complex kind of a calibration that you'll have to do to use it as a sundial. So here, by making the shadow parallel to the equator, you get this to move in such a way that in equal intervals of time you move equal distances. And then finally, how do we use this as a clock? We use this as a clock in the sense that when the sun is rising, just at the rise time, the shadow will be horizontal in the western direction. We call that as 6 a.m. sundial time. When the sun has gone to the maximum height it can go on that day, the shadow will be perpendicularly downwards. We say that is 12 noon. And when the sun is setting, the shadow will be perpendicularly horizontal, parallel here, and we call that as 6 p.m. So the shadow will make this 6 a.m. to 12 noon to 6 p.m. all days. It will do this. The sundial says that this is 6 a.m., 12 noon, 6 p.m. Our clock time, of course, is a little different. So we have, sometimes we have more of daytime and less of nighttime, and we have sometimes less of daytime and more of nighttime. And all of this is coming about because Earth, if it was going around in a circular orbit around the sun and the spin axis was perpendicular to this, we would have equal day and night generally. But because Earth axis is tilted, this is the main culprit. Earth going in elliptic orbit doesn't do so much. So because of this, Earth is going around like this and the tilted axis and it is spinning. So the net result is we see the sun sometimes moving fast in the sky, sometimes slow in the sky. So this thing mathematically we can make it what is called an equation of time, which will change this in the sense that the time that we see here, we have to correct it with respect to equation of time. We also have to change the time with respect to longitude, because each country has maybe one or two longitudes which will define the time zone. But the sundial tells the time for only that particular longitude where you are. So you have to have a constant correction, and the equation of time will be a variable correction. And so there are going to be different correction factors for a given day. At the Jaipur Observatory, for that day, the final correction factor is kept near the instrument Nadivalaya Yantra. What is the correction factor? They put it out there. And so whatever time you read from the sun, you just add the correction factor to it and you get the clock time. So it will be good to make a model of this instrument. Right now, if you are not in Jaipur or Ujjain or Varanasi, these three have the Jantar Mantar Observatory has this beautiful instrument, the Nadivalaya. So if you don't have that, let's talk about how we could make a model of it without having all the complications of this large instrument, but just the bare essential, how we can construct. So let's now talk about how we could make a simplified version of that Nadivalaya for our latitude. Because we have here, this is just a rough thing which we have started to make, and this has been actually made for about 44 degrees latitude. So what we make for our own latitude may be different. For Delhi, we are going to make for 28.5. For Hyderabad, for that latitude, any location that we want to make. So what we will need is some kind of thick chart paper with which we can make a cylinder. And actually we may need slightly larger kind of a cylinder. We need a cylinder which can make the two clock faces. And so we are going to work on how to make the clock face. And so these are only just for demonstration. The real thing will need to be a little larger than this. And we need a base for it, where the cylindrical face can rest and at the angle that we want. The crucial thing is that this angle should be equal to the latitude of the location. So we just need to make the base in such a way that the angle is, when this is going to be supported on this, we support this on this base, and so it automatically comes at that angle. And we get our two clock faces. Basically that is all that we want, two clock faces at this. So what do we do? We have made this base using just a rectangular support, and we have put this triangular piece on it, and at the moment we had cut it for 44 degree, but we will cut it for whichever latitude that we want, and this is going to rest on this. And then we are going to wrap something of this kind, has to be the clock face. This is of course much larger than our cylinder size, so we'll have to cut our cylinder in such a way that it can fit maybe something like this. This is a printed version of a protractor which has been modified for the Nadivalaya. What are the modifications? Actually I have rubbed out all the protractor. I have taken a protractor image from online protractor image, rubbed out all the 90 degree 180 divisions, and instead made the divisions which are appropriate for us, which is that from here to here we want to divide it into 6 pieces. So 6 a.m., 7 a.m., 8 a.m., 9, 10, 11 and 12 noon. And 6 pieces, 1 p.m., 2 p.m. So if this is the east, let's say. So the sunlight is coming here this way. In the morning the shadow will be here, 6 a.m. And so we have divided the protractor now into those 6 parts here, 6 parts, and they are all the equidistant parts. And we have divided 1 hour into these 3 pieces. So we have 20 minutes here, and so 20 minutes has been now divided into these 5 pieces. So the least count for this that we have is 4 minutes. And so there is going to be a small rod, or we have to actually, through this, there has to be a rod or a plastic straw, let's say, which goes through it and comes out on the other side. And so the shadow of this, let's put it, when we put it out in the sun, our instrument has to be put in such a way, use a compass along the north-south line, and the lower face to the south and the higher face to the north, and north-south line, and this will be our model Nadivalaya placed there. So we have cut out all the other features of the Nadivalaya, kept just the essentials. That's why it looks very different. Of course, these were 44 degrees, so it looks very, the tilt looks very different. So this is what we have to do: adapt an image of a protractor. Otherwise, you could of course make your own protractor. But remember that our divisions have to be such that from here to here we have to have 6 divisions, here to here, and depending on the size of this, our least count is going to. The larger this, the better the least count that we will have. But we may start with a small one and go on to making a larger one. And then we put it out in the sun, look at the shadow, read off the time from this, and then add the correction factor for the day onto this. If you actually just look up online what is the solar noon time for your location, because these resources are now available very easily. What is the solar noon time? So what is the difference from 12 for the solar noon time for your location for that day is the correction factor. So you just have to do that, and you have your sundial.